Okay, this lesson is on functions, and it's part of the Integrated Algebra Standard AA21. Determine whether a given value is a solution set to a given linear equation in one variable or linear equality in one variable. So the topic today covers this within the discussion, but it isn't the main part of the lesson today. Vocabulary is domain, range, function, independent variable, and dependent variable. Okay, so first we're going to cover relation, and actually relation should be a vocabulary term too. So a relation is a set of ordered pairs. So for instance, if we had this set of ages and a set of people, so let's say that you had some people who were 17, 18, and 19 years old. So let's say that we had a couple of people. Let's say that we had Tom, and Tom, let's say Tom is 17, and let's say that we had Harry, and Harry, let's say Harry is also 17, and let's say that we had Belinda. Let's say Belinda is 19. Okay, so the set of ordered pairs that these would be this information would create would be 17, comma Tom, 17, comma Harry, and 19, comma Belinda. Okay, so a relation is just something that relates one set of objects to another set of objects. Okay, in this case, the ages are what we consider the domain. They're what we take from. And the people are considered the range. Okay, and when you look at the ordered pairs, the domain is always going to be the first coordinate, and the range is always going to be the second. So it's always going to be domain, and then range. Now, these are just, domain is a set of values from which we start with, and range is a set of values from which we end up in. And it's going to be a little bit more clear when we have functions what the domain and range is. So let's think about the relation greater than. So greater than is a comparison of the value of two numbers. Created ordered pairs where the first element is greater than the second element is greater than the first element. So let's think about this. So if our domain is 1, 2, 3, the set of 1, 2, 3, and 4, it means that's the numbers that I can take. So I always want the second element to be greater than the first element. So one possible situation is 1, comma 2, because 2 is greater than 1. I couldn't put 1, comma 1 because 1 is not great. It's not true that 1 is greater than 1. 1 is greater than or equal to 1, but it's not greater than 1. So 1, 1 is not an element of this relation. Okay, remember, a relation is a set. So with set notation, I use the curly bracket. It's a set of ordered pairs. Okay, so my first element in my set is the ordered pair 1, 2. Okay, and then the next element I could go to 2, comma 3, and then I could go to 3, comma 4. Okay, I could also have, let's see, 1, comma 3, or 1, comma 4, and I can have 2, 4, and I believe that's it. So I'd end my curly bracket. Okay, so I have the elements of this particular relation greater than are 1, 2, 3, 4, 5, 6. Okay, so the domain was this set of numbers, and the range is actually the set of ordered pairs. So the range is the set of, so these are all elements of the range. It's a little strange because the domain is numbers and the range are ordered pairs, but that's how it would go in this situation. Now, a function is a special type of relation where no two ordered pairs have the same first value. They can have the same second value, but they can't have the same first value. So for instance, the relation that we just looked at would not be a function because right here, this ordered pair and this ordered pair and this one, in fact, have the same first element. And this one have the same first element. So this particular relation greater than is not a function. Okay, another way to say this is that each element in the domain is paired up with only one element in the range. So when we look at our oval description, so sometimes we like to represent the domain and the range as elements in an oval set here. So let's look at the way that we diagram these two functions and see which things below go with the function, the idea of function. So these are all relations, by the way. Picture 1, picture 2, 3, and 4 are all relations that are just not all functions. Okay, so for the first one, look at the way that this is set up. So this is set up so that, and I should have arrows here. So like a relation sends one number to another number. So the first thing, 1 gets sent to R. Okay, so far so good. The next thing is 2 gets sent to S. And the third thing is 3 gets sent to T. Okay, so let's check our understanding. A function is a relation where no two ordered pairs have the same first value. So none of the ordered pairs in the first diagram, none of the ordered pairs have the same first value. So this is a function. Okay, so if we were to relate the next one, 1 gets sent to R, see, 2 gets sent to R, and 3 gets sent to T. Okay, so no two pair has the same first value, and I look and I have 1, 2, 3 as my first values here, 1, 2, and 3, so this is also a function. Notice it's okay if not every element in the range is part of the relation. So in this case, S was not part of the relation, but that's still okay, as long as the first coordinate is not identical in any of the ordered pairs. Okay, for the next one, here 1 goes to R, so that's the arrow notation. 1 goes to R. 2 gets sent to R. That's that arrow right there. But 2 also gets sent to S. Okay, and the last arrow says that 3 gets sent to T. Okay, now this isn't, by the way, like something, it's not an equation that we know about. It's just a visual description of what this relation would do. Okay, it's sort of a nonsense relation, but it's just a way to sort of describe to you the relations that are functions and the relations that are not functions. So I know that it seems a little strange when I say 1 goes to R, because what does that mean? But it's just a visual description of what a function can be. Now in this situation, since 2 and 2 are identical, this thing is not a function. Okay, because this particular relation sends 2, let's look at it again, it sends 2 to 2 places. It sends 2 to R, and it also sends 2 to S. Okay, so it is a relation, but it is not a function, because 2 can't go to 2 places. It can only go to 1 place. Okay, notice that it was okay that 2 different numbers went to the same place in the thing before, but it was not okay for one number in the domain to be sent to 2 different numbers in the range. Okay, let's check out this this domain and range here. Here, 1 gets sent to T, and 3 gets sent to T. All right, so 2 was not used and in the domain, and R and S was not used in the range. But our definition of function is still okay, because neither 1 nor 3 are the same. So there's no ordered pair in this relation that has the same first value here. So this is a function. So 3 of them are functions and 1 of them is not a function. Okay, the first element in the ordered pair is what we call the independent variable, and the second element in the ordered pair is called the dependent variable. And we're going to use that a lot more when we talk about x and y coordinates. Okay, x is considered the independent, and y depends on x, so it's considered the dependent. Okay, so if we are asked to find 5 members of the relation 3x plus y equals 7, that means, remember, the relation is a set of ordered pairs. and I'm looking for these sets of ordered pairs that make this true. Okay, so which ones make this true? Well, let's just choose some x's and see what we get out for some y's, and that would create some situations that I know are true. So actually, it's probably a little easier to have one of these variables on one side. So let's solve this equation for y. Let's try to get y by itself. So the first thing I would do is I'd subtract x from both sides because I want to get y by itself. So let me subtract 3x from both sides. So we'd have y is equal to 7 minus 3x. Okay, it's a little easier. Now let's put some numbers in for x. Let's put, 1 in for x. So 7 minus 3 is 4. So one element of the relation, so I'm going to write it as a set. One element is 1, 4. Okay? All right, let's put let's put negative 1 in and see what happens. Okay, so y is equal to 7 minus 3 times negative 1. Okay, so 7 minus 3 times negative 1 is negative 3. Okay, 7 minus negative 3 is 7 plus 3. So y would equal 10. Okay, so y would equal 10. So when I put negative 1 in, I arrive at 10. So that's another negative 1, 10. Okay? And so I could continue to do this. Let me put 2 in there. So y is equal to 7 minus 3 times 2. Y is equal to 1, right? Because that's 7 minus 6. So another member would be 2, 1. Oops. And let's see, okay, let's put 3 in there. Y is equal to 7 minus 3 times 3. So y is equal to 7 minus 9, which is negative 2. So 3, negative 2 in there. And let's put another negative number in there. Let's put negative 2 in there. So y is equal to 7 minus 3 times negative 2. So that's 7 minus negative 6. So that's 7 plus 6, which is 13. Okay, so we have comma, negative 2, 13. Okay, and we'd end with a curly bracket. And the question is this relation a function? Now, remember, our definition of function says that none of the first elements can be the same. So let's look at our first elements here, the first element of the coordinate pair. None of these are the same. But how do I know that this is always going to be the case? Well, whenever I choose a value for x, I'm going to run it through this equation, right? So I'm going to run it through this right here. So any value of x I choose, is there any possibility that if I chose some value for x, it would come up with two different values for y? The answer is no. If I choose 1, I come up with 4. If I chose 1, it couldn't suddenly come up with something else because I run it through some sort of computation. And so whenever I put 1 in here, I'm going to come up with a specific number. In this case, I'm going to come up with 4. So every particular x that I put in here, I'm going to come up with some different y. Okay, so the answer to this was yes, this relation is a function because none of these first elements are going to be sent to two different places. Right? Whenever I put something in for x, I'm not going to suddenly come up with 2 and 3 or 4 and 5. Okay, so if you're asked to determine whether each of the given ordered pairs is a solution to the inequality, this is something that you might be asked to do, right? That was part of what the learning standard was for this lesson. So let's see. All you have to do, we've done this before. This is the part of the discussion about solution sets. Substitute the values of x and y into the linear inequality and see if it makes it true. So is it true that 0 minus 2 times 4 is greater than or equal to 0? So that 0 minus 8, is that true? And that's no, because that's negative 8 is not greater than or equal to 4. Okay, so that's not. Let's try the next one here. Is it true that 2 minus 2 times negative 1 is greater than or equal to 4? 2 minus, that's negative 2 is greater than or equal to 4. So that's 2 plus 2, and that is true. Okay, so that's a member of the, it's a member of the solution set. It's also part of the relation. Okay, those are two identical ideas. Okay, so we have we have 6 minus 2 times 0 greater than or equal to 4. And that is true because that 6 minus 0 is greater than or equal to 4. And the same thing goes with 7. Is it true that 7 minus 2 times 0 is greater than or equal to 4? And that is true. Okay, so these are all solutions to the inequality. These are all part of the solution set to the inequality. And they're also elements of that relation. Okay, so we're just going to go over a couple word problems, and then the lesson will be finished. So let's say the cost of renting a car for 1 day is $64 plus 25 cents per mile driven. Let X represent the number of miles the car was driven, and let Y represent the rental cost in dollars for a day. Write equation for the rental cost of the dollars in terms of the number of miles driven. So in terms of, this means that the variable we're going to use is the one that follows that statement. So if we're doing it in terms of the number of miles driven, so it's going to be in terms of X because X is the number of miles driven. Okay, and Y represents the total cost. So the total cost is equal to, okay, now this right here, this 25 cents, is your variable. That's going to be associated with your variable because that's per mile. That's your per mile fee. So that's dependent on how many miles. The $64, that's just a constant cost. That's not going to change depending on the amount of miles you drove. So the way we set this up is Y is equal to, okay, the per mile cost is 0.25, and we're going to multiply that by the number of miles driven. And then to that, we're going to add the $64 that it costs per day, or for 1 day. Okay. Now we can use this equation to find the missing members of each of the following ordered pairs. Okay, we are given that they are elements of the solution set. So we know that that's very helpful because if they weren't elements, we'd never be able to find what that well, there'd be a lot of different things what that question mark is, but it wouldn't be, I couldn't find it using this equation. Okay, so here I'm missing my Y, so here I got to put in X. So this is saying, since X is the number of miles driven, it's asking you what the total cost is, right? The total cost is missing. It's asking you what the total cost is if you drove 155 miles. So you have Y is equal to 0.25 times 155 plus $64. Okay, so here to figure out what 25 cents times 155 is, I divided 155 by 4 because there are 4 quarters in a dollar, and I end up getting 38.75. Okay, so I have 38.75 plus $64 gets me, let's see, 75, 97.75. So the total cost would be 97.75. So if you drove 155 miles, your total cost would be 97.75. Okay, and to find the last one, I would try to figure out, that's asking me, okay, if you spent $69, if your total cost was $69, how many miles did you drive? So we'd set it up this way. Okay, well, out of $69, let's subtract this daily fee, which is $64. So $5 is spent on the per mileage fee. Okay, so let's divide each side by 0.25. So it might be easier actually to represent that as a fraction. So 0.25 is 1/4 X. So to get rid of that as a coefficient, we multiply by 4 over 1. Okay, so X would be equal to 20. So they drove 20 miles. So at 20 miles driven, the cost per day is $69. Okay, and that's the end of our lesson. So today we talked about relations, and we talked about a particular relation, which was a function. We also reviewed how to tell whether a given value is a solution to a given linear equation in one variable, or an inequality in one variable.